Hello everyone and welcome back to this new video of Agentic AI series. Today we are talking about Agentic DevOps. So we are shifting from building agentic systems to something more complex and far more critical at the same time, which is operating agentic systems in production environments. Up until now, we focused on components, architecture, frameworks, but none of this matters if the system cannot be reliably deployed, monitored, and evolved in production environments. So today we are not discussing how to build agents anymore. We are discussing how to operate them reliably in production. Agentic DevOps is mainly about managing evolving agentic or intelligence systems, observing behavior and not just execution, controlling systems that are inherently non-deterministic. So are the main characteristics of the agentic DevOps. And in reality, this is where most real-world AI systems fail, not at the model level, but at operation level. So let's clearly first position where we are in this evolution in general. Traditional DevOps assumes a stable world where code defines behavior, behavior is predictable, and testing validates correctness. The next came machine learning operations, ops, ML ops, which introduced a layer of uncertainty where models behave in a probabilistic manner and data became a dynamic dependency of the system. But agentic system introduce something fundamentally different. They plan dynamically as they are goal driven instead of being instruction driven. They interact with tool with the external world. They maintain state. They are context aware instead of being stateless. They are adaptive and they evolve through across time instead of being fixed. This means that the system we deploy is not fixed in time; it evolves through prompts, through interactions, through feedback loops, etc. And this means that we are not anymore deploying logic. We are deploying a system that generates its own logic at runtime. Agentic systems break assumptions at every layer. They introduce non-determinism. For example, identical inputs can produce different outputs. There are multi-step reasoning where execution unfold dynamically. Tool interactions, external dependencies influence outcomes. Memory, where past states shapes future behavior, and multi-agent dynamics where behavior emerges from interactions. This creates a critical implication, which is we cannot fully test all execution paths. We cannot fully predict system behavior, and for sure, we cannot fully isolate failures. Failures become emergent, not explicit in such systems. And this is why DevOps must evolve into something closer to behavioral system management. In traditional ML systems, versioning is already more complex than software. But in agentic systems, it becomes multidimensional. An agent is not a single entity, but it's a composition of interacting components, a foundation model, a prompt template or prompt templates that shape the reasoning, tool APIs that extend the capabilities, memory systems that provide context, orchestration logic that defines execution flow. Each of these evolves independently. And now think about this. If we change the model, reasoning changes. If we change the prompt, behavior changes. If we change the tool, capabilities change. If we change the memory, decisions change. So what exactly are we versioning here? Not the model, not the code, for sure, we are versioning a behavioral system configuration, and this leads us to a new requirement. So versioning here must capture component states, interactions between components, and observed behavior under certain circumstances, under specific scenarios, and so on. Prompt versioning as a first step. Usually, prompts are treated as simple strings, and this is a mistake. In agentic systems, prompts act as behavioral policies, reasoning scaffolds, decision constraints, and any subtle change in phrasing can alter reasoning depth, can change the tool selection, introduce or remove hallucinations, and this makes prompt management critical actually to our agentic system. And some best practices include here to treat prompts as structured artifacts of the system, to store them in version control systems, associate them with specific model versions, because one prompt works with this a specific model and a specific model version that cannot work with another version properly, for example. Track performance metrics per prompt version and per associated model version as well. In advanced setups, prompts become modular, composable, and dynamically generated. And at such point, we are no longer writing prompts. We are engineering behavioral programs. Reproducibility is one of the most misunderstood aspects of AI systems. In traditional systems, same input, same output. That's simple. In agentic systems, same input produces a distribution of possible outputs. And here, reproducibility becomes statistical. We aim for consistent behavior patterns, we aim for stable performance metrics, and we aim for predictable failure modes. To achieve this, we need deep observability. And for that, we have to log everything: inputs, prompt versions, model versions, tool interactions, intermediate reasoning steps, etc. And without that, we cannot debug failures, we cannot compare versions, we cannot improve systems, and so on. So here, we need to think about reproducibility as not reproducing outputs, but exactly as reproducing behaviors, which is the main character of the agentic systems. The tooling ecosystem is evolving rapidly to capture and support this shift. Platforms like weights and biases enables experiment tracking and prompt logging. MLflow provides model registries and lifecycle management. Langsmith, one of the most famous ones in the agentic AI ecosystem, focuses on tracing agent executions. Hugging Face, for example, supports model and dataset versioning, etc. Such systems, such platforms, etc., are moving beyond traditional experiment tracking. They now capture prompt execution, agent traces, behavioral metrics, and so on. The shift now is from tracking artifacts to tracking intelligence behavior. Observability must evolve from system metrics to behavioral insights. Traditional monitoring answers: is the system up? Is it fast? Etc. While agentic monitoring asks: is the system reasoning correctly? Is it making good decisions? Is its behavior degrading over time or evolving over time? Um, we need to understand this is a fundamental shift. Observability here becomes a window into cognition. To understand agentic systems fully, we need to observe them at multiple layers. Infrastructure layer on GPU utilization, latency and cost, model layer on quality of output, model drift, hallucination frequency, and so on. At agent layer, tool success rate, planning efficiency, tool usage pattern, and so on. Interaction layer, user feedback, correction frequency, and trust signals, etc. Each of these layers reveal a different failure mode. And we need to keep in mind that most critical failures are not visible at one layer itself or alone. They emerge at the behavioral level, so they might be uh, compound failure across these layers, all of them together. And to understand agent behavior, we need to keep in mind that the agent execution is not linear. It's iterative, it is going through branching and context dependent, etc. And this requires tracing systems that capture reasoning steps, tool calls, intermediate outputs, and final decisions. We know LangSmith, which is part of the ecosystem of LangChain, provides this capability. And such tracing allows us to debug reasoning failures, identify inefficiencies, and improve planning strategies. We know that without tracing, agent systems become opaque and uncontrollable, and we don't want them like that, for sure. And for all of that, evaluation must move from being offline to continuous. Instead of evaluating the system once, here we have to evaluate every deployment, every interaction, every behavioral shift. And this includes scenario based testing, real world task validation, human in the loop feedback, etc. Important to think of evaluation as a monitoring system, continuous monitoring system instead of one snapshot assessment, as a feedback loop, as a governance mechanism. Key tools in this space include Langsmith, as we said, Aries AI, YLabs, OpenTelemetry, which enable drift detection, behavior monitoring, distributed tracing, etc. Important to notice that these tools or the ecosystem is converging towards unified AI observability platforms, like kind of a full stack AI observability. And this evolution is happening rapidly, and we need to keep an eye on the evolution as the time passes. Infrastructure as a code. Agentic systems rely on complex infrastructure. GPUs for computing, vector databases for memory, API for tools, distributed orchestration, and so on. So manual configuration leads to inconsistency, reproducibility, and scaling issues. Infrastructure as a code solves this. Some tools like Terraform, Pulumi, etc., allows us to define infrastructure declaratively, and infrastructure here becomes version, testable, and reproducible. Let's briefly break down the core infrastructure stack behind agentic systems. At a high level, it consists of three main layers: compute layer, where models and agents run typically on GPUs or scalable inference endpoints; storage layer, which includes object storage and vector databases used for memory and retrieval; serving layer, where APIs and orchestration services manage agent execution and interactions. What makes this stack unique is not these components themselves, but it's how tightly coupled they are. For example, retrieval quality from storage layer directly impacts reasoning. Compute availability affects planning depths and execution path. Serving logic determines how agent coordinate multi-step tasks. So the system behavior is shaped not only by the structure or architecture of each of these layers, but by how these layers interact among each other. Given this complexity of the agentic infrastructure, managing the infrastructure manually is not viable, as we said. This is where infrastructure as a code becomes essential. Tools, as we said, like Terraform or Pulumi, AWS, Cloud Formation, etc. We, with these tools, we can define infrastructure in a declarative manner and version it alongside our system, and this allow us actually to reproduce environments consistently, scale resources dynamically, align infrastructure change with model and agent updates, etc. Without infrastructure as a code, even small environment differences can lead to completely different system behaviors. In agentic systems, infrastructure is not just support, it directly influences how the system behaves. CI/CD, continuous integration and continuous deployment in agentic systems, goes beyond traditional software pipeline. In classical systems, pipeline focus on code, and that's simple. In AI system or agentic systems, they must handle code, data, models, prompts, etc. And each of these can change independently, and each of them can affect system behavior. This means that our pipeline must validate not only the correctness, but the behavioral impact at the same time. So important here to understand that CI/CD becomes a mechanism for continuously validating evolving intelligence, and not only to as a mechanism for deploying code. To support this, AI pipelines include three stages: continuous integration, which includes validating data schemes, testing prompts, and running evaluation benchmarks; continuous delivery, which includes deploying agents to staging and production with controlled running and rollout strategies; continuous training, which includes updating models, embeddings, and knowledge bases as new data becomes available. These stages are tightly connected, and for example, any change in the data may trigger retraining, any change in prompts may require reevaluation, and so on. So the pipeline here becomes a continuous loop of learning, validation, and deployment. Testing in agentic systems becomes fundamentally different, as you could see throughout this video. Here we are not just testing functions, we are testing behaviors. This includes task success rate, handling of edge cases, robustness under uncertainty, and testing becomes scenario based rather than input output based, focusing on outcomes instead of exact outputs. The goal in agentic systems testing is not to verify exact responses, but to ensure reliable performance across situations. Because behavior is uncertain, deployment must be controlled and incremental. Common strategies include shadow deployments, where new versions run alongside existing ones, canary releases, where updates are rolled out gradually, A/B testing, where different versions are compared under real conditions. These approaches allow us to detect behavioral differences early, reduce risk in production, and continuously improve system performance. Deployment here becomes experimentation under controlled conditions. Supporting this pipeline requires orchestration tools that can handle complex workflows. Common tools include GitHub Actions for automation and pipeline execution, Kubeflow for ML pipelines, Airflow for scheduling and orchestration, etc. These tools enable automated validation and deployment, integration of data models and evaluation, scalable pipeline management. Important here to see that tooling layer becomes the backbone of continuous intelligence operation at this level. Despite all of these practices and tools, agentic systems introduce fundamental challenges that are not fully solved. First, non-determinism, which makes behavior hard to predict and debug. Second, there is an evaluation gap where we lack standardized metrics for measuring agent performance. Third, cost can grow rapidly, driven by token usage, API calls, and compute demands, etc. And finally, and most importantly, safety and alignment risks, where agents may behave in unintended or undesired ways. These challenges are not edge cases, they are inherent to how agentic systems operate. The difficulty is not in building the system, but it is in controlling its behavior over time. These challenges require a fundamental shift in mindset. We move from managing static systems and deploying fixed logic to governing adaptive systems and managing evolving behavior. This means thinking probabilistically instead of deterministically, focusing on behavior instead of outputs, treating systems as dynamic rather than fixed. Agentic DevOps is not just a set of tools, it's a new way of thinking about systems that learn, adapt, and evolve across time. At this point, we can step back and see the full picture. Agentic DevOps is not just an extension of traditional DevOps or even ML Ops. It represents fundamental shift in how we think about systems. As we saw, we're no longer deploying static software. We are not managing predictable behavior. We are observing reasoning processes. We are managing emergent behavior. We are controlling systems that evolve over time. This changed the role of operations entirely. Operations here is no longer about uh, support function. It becomes actually as a core layer where intelligence is governed. And this leads to the real questions that define success in agentic systems. Can we understand how the system is making decisions? Can we trust its behavior under uncertainty? And can we control how it evolves over time? And because in the end, we are not operating a software, we are operating a living adaptive system. And as we see here in our famous slide, we covered today agentic DevOps. And as we said, because we are not operating static software and we are operating adaptive, living adaptive systems, we need to see in the next video more about safety and governance to ensure our systems or agentic systems are reliable in production environments. Until then, thank you for your time and attention, and see you there.